Okay, so in the name of God, the compassionate, the merciful, this is the second session on C++ template metaprogramming. The first session introduced function templates and also class templates, and now I am going to give you your entry to what I meant by saying that C++ template metaprogramming is in fact dependently typed. So there is something in C++ TMP, and that's a common acronym for template metaprogramming, that is referred to as non-type template parameters. So you have seen things which you can pass as the template argument to template functions, or to function templates, or to class templates, and you have seen that in all of those occasions you were passing types, except for one occasion. I just recalled that you have seen one occasion. Perhaps you didn't notice it. Now, today we are going to start by focusing on those parameters that are not types. So imagine the old stack template class that we were dealing with, but this time we wanted to also have a size that is statically defined. So we would like to be able to say that I want a stack of integers of at most 20 elements or 40 elements, right? Now, in order for you to be able to do that, then you will need to also pass this size as a parameter to your class template, and the thing is that it's the difference between when you are passing a type is that, when what you put in the angle brackets in the class definition is now instead of this keyword type name, you would provide the type of the compile time value that you are passing. And given that this thing is no longer a type, it is referred to as a non-type template parameter, right? Now, so you see, this is probably similar to the address that I am highlighting down here, right? Where you get a type, which is this. You provide a nat, which is this one, and in return you get a type, which would be your stack of choice. So stack itself is higher kinded, both here and here. It's not still a type. It will only become a type when you provide the two parameters that it expects, one of which being a nat in the case of Idris. So you see that in the case of Idris, a type and a non-type value sit nicely together. The same is going on here. And that is the entry of what I meant by saying that, there is dependent typing there. Now, so function templates can also have non-type parameters. So for example, I might want to have a function that takes what is happening? Right, that takes a compile time constant value, and it also takes a type, right? For the type of the argument that is going to be passed to it, and all it does is that it adds that that value to the argument that it receives, and it returns it. Now, we'll start by a few things here. First of all, the equivalent Idris is something like this. This is still a pseudocode, right? It's not entirely Idris, but it's very similar. So this is a function that takes a type, an integer, then a type, and then an instance of that type, and it returns an instance of that type. Right? Now, what you see here is that in Idris, there is no these two don't sit higher up. They sit at the same level with the val. Actually, it's these two, right? And it should be, by the way, it should be val and then type and x. It's the other way around. I should have written it val tie x, not x tie val. Whereas in C++, there is a distinction between the things which need to be provided at compile time and the things that need to be provided at runtime. Now, what is here, right? The things which are inside the angle brackets, they need to be provided at compile time. This one, the x, can be provided at runtime as well. And I think I witnessed my first yawn from Jan. No, you killed it?
I simply opened my mouth.
Okay, doesn't count. Okay. So that means that, well, first of all, you can't pass runtime values here. Secondly, there are limitations on the types that you can put here. Now, the C++ committee has worked hard on lifting the what is it called? The restrictions on the types that you can put here. And they have I would say they have done a great job. I remember those old days when there were essentially only integers here. But now it has been relaxed by much. So if you have a literal type, which I'm not going to get into, but it's great read if you want to, then you can put it here. So that's one thing. The other thing is that you notice that there is a I'm trying to put requirements on this type, right? And that's because I am going to use it this way. Now, this is not entirely Idris, because like we discussed the previous time, the plus is between two things, and this nat is only a requirement on one of those. It's the requirement on the type of one of those. It has to be, in reality, it has to be more complicated than that. But the C++ mindset was that because of the two-phase translation, so long as the type that you instantiate this add val function with does support an addition with int, you're good, right? And that you only know when the type T is provided, because this is type dependent deduction, right?
I have a
Now you
question.
can, please.
Can you replace the int in the template with a T?
Yes, you can, but that would be a different thing.
Yeah.
Right. Yes, you can. We'll see examples of that. Yes, you can. But if you want to do that, then you have to reverse the
So the
order.
template order matters.
Yes, yes. So that would have been type name T and then T val.
Yeah.
Right? Yeah. Jan, you wanted to say something?
Oh no, I was going to say that there is a parallel with the Idris code then. It
Yes.
says that the ordering matters in the same way as the ordering of signature matters.
Correct, yeah. Now, so there is something called, like we discussed in the previous session, there is something called C++ concepts that I typically don't cover. I might cover for you guys now that you're this good, that allows us to enforce similar things on the type T that is going to be instantiating this add value function here. But that is not a requirement by the compiler. That's something that it is optional to the C++ TMP program. Now, right, Idris in Idris 1, I don't know what is happening to my PDF, but do you also get that strange impact when I highlighted it just shows something else initially? Now, anyway, so in Idris 1, everything was runtime, right? And the compiler would do some clever things to figure out that certain things can be moved to compile time. But the programmer didn't have a say in that. Whereas in Idris 2, they added something called quantities. So like I alluded to a few sessions ago, you can annotate certain things in Idris with their quantity, and if that quantity is 0, then it's compile time. If it's 1, then it's runtime, and that's the way that the programmer can enforce, if the rules are followed properly, the stage in which something exists. Now, so like I said, before C++ 20, you could have, for example, you could have not put double here, whereas right now you can, but you have to be careful about the version of C++ that your compiler is using, and we'll go through that in the practice sessions, right? Now, C++ 20 released all, but not all, but most of those restrictions. Not all of them are, like I said, it has to be literal type that you can put the. I'm not going to give you the exact details of what that means, but it's be careful that not everything can sit in the place of that int. Now, the other thing is that you can leave the type of this thing to C++, by doing which you won't be bound to ints, but you will be bound to every acceptable type, and it's for the C++ compiler to figure out which one you are using. So, for example, you here with 20U, it is using up to 20s of 20. This U is for unsigned, right? Now it doesn't really make sense in this very example to have something of -40, for example, right? But if you put an auto over there, then so long as what's up here matters, you can pass a -40 to the class template as well. And if you do so, and you want to know the type, the exact type, which is going to be used. So for example, in this case, you want to know that it's an unsigned int, then this is the way you do it. So you say that I want to know the declaration type, the decl type of max size, right? That gives you, that makes this size type, in this case, unsigned int, right? Now, before C++20, this would have not been possible. Whereas now this is possible, although you would be stopped at the point where you try to instantiate the underlying container. So for example, here, so when you want to instantiate an array of type T of maximum 3.14, you will be stopped because then your 3.14 is not applicable here. Okay, that was our first touch of non-type template parameters, and you now have some understanding of what I meant when I said that C++ metaprogramming is dependently typed. The idea is essentially that up there in the angle brackets, types and values can sit tightly together. There is nice and tight together, and there's no restriction on what you put where. Any questions thus far? Okay. Now let me see, who is it that I'm missing? Right, Mikhail. Would you mind giving us your joke, please?
Oh, why did the developer go broke?
No idea.
He lost his cash.
Right. Okay. Yeah, good one. Good one. I initially thought that you were going towards breakpoints and all that.
Oh,
But yeah, but no, it doesn't seem to be that. Okay. Let's see.
Nobody
I'm going
debugs
to
their
go
code.
somewhere. Yeah, that also occurred to me, but I thought that okay, that's not funny. Yeah.
No, in the sense that breakpoints are the debugging thing, and all you need are print statements, all you need are print statements.
Right. Yeah. You'll get past that when you're deep in the industry.
No, fair. I know.
Yeah. Niels, would you mind helping us with another, please?
A joke?
Yes, please.
I didn't have any,
you have not prepared any.
I can say that whatever the joke I was telling is the one Sander is going to tell, unfortunately.
Okay. Then you owe him something for the next session.
Yeah.
Okay, Sander, do you accept that lending?
Okay, you want me to tell 2 jokes now?
No, just one of them for
just
now.
one? Okay.
Yes.
How?
Oh.
Actually, let's do a quiz question today. Mostly because I can't think of any jokes.
Oh, I have one though.
There is a single ATM in the world that will let you conduct transactions in Latin. Where is it?
The Papal State.
That's completely correct. Yeah.
Let's go.
Hmm.
Let's go.
There's ATM there I think it's only one that will let you do.
I guess
So
that's
this is-
the
this is
common
for
language of the
reality.
Cardinals.
Yeah, I was going to guess like
I think it's more
close to the Bunpris near the Alfagsbygget, because you can
oh yeah.
at the self-checkout you can choose Latin as a language.
Oh,
Really?
is
I think it was
I think it's more of a novelty thing. More than anything else, but it makes sense.
So let me. I'm not sure I understood this. That's in Vatican. So in Vatican, there is a
There
is
is,
an
or at least there
ATM.
was. Yeah.
There was an ATM that was in Latin. Okay.
Or yeah,
But-
you usually have a selection of languages, right? You have English, probably
Right.
Italian,
Okay.
probably a
if
bunch
you-
more since it's the Vatican. But yeah.
if you consider
Okay.
it, the inhabitants of the Vatican can come from all kinds of countries, but the ecclesiastical language of the church or the Roman Church is Latin.
Isn't that? Yes. Yes.
Yeah,
right.
exactly.
Yeah, you're right. Yeah. I have a colleague from Wales who once upon a time, when was in Eastern Germany, he had to go to the emergency, and he doesn't speak any German, but then he managed to communicate with the doctor because he spoke Latin.
Wow.
We
And-
Latin. Yeah.
Yeah, and Latin is perfect for what for medical terms and all that. So
It's
he managed to survive, the East German medical system.
wonderful. Latin is a great language to know. It's definitely not
I-
wasted on the youth of various private schools.
I went to one of those private schools, and Latin was an option you could take there. Yeah, it was a Catholic one, so that explains it. We also had Italian. That was my foreign language.
Which we know you speak with a certain accent.
Yes.
Yeah.
The Pyrenees one.
Okay. Now, back to business. Now, this is the point where things start to become exciting. This is something that was not before C++ 98, and it came out as a response to a need that people had felt, and that they were so much in need of, or so much in favor of, that they had hacked the template system of C++, and that was such a demanding task. It was, I do recall that time, and I have been a part of that. But nowadays, Variadic templates actually make that so easy. Now, so the idea is that, with, oh, sorry. My cursor was at the wrong place. Now, you can have a print function, and you guys now probably remember that we did the printf, the type safe printf, right?
Mhm.
You can have a print function that takes any number of arguments, and it needs to be type safe. Well, the way that you would do that would that you would want to have some way of passing the types, or having the types deduced by the compiler for you, but the number of those types has to be able to vary, right? This is where Variadic templates come in, right? Now, I will start from here. Now, so let us say that you have a, well, no, I'll start from here. Let us say that you have a first argument that you would like to print, which is of a type T, and you have more arguments which are of a number of types, right? And all you would want to do is that you would want to print the first one and then recursively call the function for the rest of your arguments, right? Now, of course, this will at some point, hit the empty list. So that's the reason why the base case also needs to be available. There are two overloads here, one of which being parameterized by types, and the other non-parameterized. Now, quite a number of things to grok at this point. First of all, this piece of syntax at the type level means a number of, and this is a number of, ellipsis is the number of, a number of types or type names packed into the name types, right? So that's at the type level. Now at the value level, you're saying that, okay, I also want a number of arguments of the right types. Now this is such a crooked syntax. It's probably very misleading, I understand, but unfortunately this is the way it is. So a number of type names called types, a number of arguments, and this is a number of a number of arguments, called, well, of types. And so each of these, the people in here, each of them, the first argument in the args is of the first type in the types. The second argument in the args is of the type of the second type in the types, right? And so on and so forth. Now, this is similar, but not quite to this, Idris. The thing is that Idris doesn't have Variadic types. So this is a piece of syntax that I myself, added. I'll give you some time to try to figure things out. And if there is a question, I'm more than willing to answer.
So,
Sander, are you good?
Yeah, I'm looking at it.
Okay, and is everyone following what's going on? Yeah. Okay. I understand that the syntax might be very intimidating. I do apologize. Unfortunately, there is nothing that I can do about that. Now, let's proceed. So this is referred to as a parameter pack, right? And the other thing, by the way, that I forgot to mention to you is that in Variadic, so everything that I say from now on, when there is something followed by ellipsis, this is being Variadic. It no longer means something. It's a part of the C++ syntax. I think that on these slides, yes. So you see, these are not a part of the syntax. This is me hypothesizing, whereas these are a part of the C++ syntax for Variadic templates.
So the ... is sort of like a list on the type level.
Well,
Yeah.
this is like a vector of C,
Yeah.
for the reasons that we always see, but it's not it's not quite a list. It's not quite a vector because it doesn't have the indexation of, but it's, we'll see that it's more like a vector. Right?
Yeah, because it's
it knows its size, and you can work with that size in the same way that you can work with the sizes of vectors in Idris.
Right on.
Right. Yep.
Right on.
Now, was there a comment that I missed?
No,
No?
Nils was just agreeing with me.
I see. Very good. Now, so yeah, this is at the type level thing. So this is a parameter pack at the type level. Now, args is a parameter pack at the value level, right? With the corresponding values of the individual types. What else? Right. Now, you see here there is no ellipsis, which is the name for ... right? Now there is no ellipsis after args, but when you want to pass args to another function, you are required to put that, because you are required to unpack your parameter pack, right? Now, if you forget doing that, it means that you are trying to pass a single parameter to the function. So for example, if I leave out the ellipsis here, it would be like I am sending a single parameter called args to print, which we don't have a function for, right? I think that's pretty much everything for that example. Now, Variadic templates can also be overloaded. So, in particular, we could have had you know, a print function that takes one argument, like the one that you were familiar before the session. You were familiar with before the session, and you can have one that takes more than one. Right? Now this one takes one as its first argument, type parameter, and it takes a number, and remember that number can be 0, right? A number of others as its later, as its more parameters. And then at the value level, it takes one instance of that type and more instances of the more types. And it performs you know, the printing by printing the first one, which will make a call to this overload, and then recursively calling itself, which would be a I will leave that one as a question, in fact. So which overload will this line call, the first or the second? And I'm going to ask that from James.
So, sorry, which question? I was zoned out.
Okay. Now the question is this. We have two overloads.
Yep.
Which
Right.
overload will this one call?
Surely the second.
How do you come to that conclusion?
Because so the reason is because I think args ... is going to, that doesn't represent a single parameter, that represents the rest of the args. And I think so.
Yes.
The first
yes.
thing in args is going to go into first arg. But I think when args has one element in it, then it will call the other one. Because I think
true.
that's like a macro in a way, where it's just going to be replaced with those parameters.
Well,
I'm coming from
macros are,
C macros here.
yes. Macros are very unsafe.
Yes, yeah. This is not a macro, but I think it behaves the same as the C preprocessor in this case.
Yes, similar, right? Similar to that. Yes, that's right. That's true. So, provided that we call this second overload with two arguments, then the call on line 14 will be a call to the first overload. If we call it with a large enough, if we call the second argument, the second overload with more than one argument, then it will repeatedly call the second argument until it's time for it to do with two. Right? Now, here is another question. Does this implementation cover all the cases that the previous implementation does? So this is our previous implementation. And this is the second one. And this is a question for Daniel. You can tell me to go back and forth between the two.
I'm guessing if it's empty in args.
That's true. That's true. So this implementation has no instruction for when you pass no argument, right? Whereas this one does. This is the overload that deals with no arguments passed to print. Now, thank you. Now a question for Niels. Will this line ever fail?
No, because the only way it fails is if args the argument you pass in is or args is empty, and it won't be empty because then it will use the other implementation of print.
That is true, but how did you know that?
Because as James mentions with the when with the macro or the macro-like behavior, that when args is just one element or just one argument, then it gets sent to the other one.
Okay, well,
and then I tried to do it. I tried to create, think about the scenario where it would be empty, and if you just do one argument, then it gets sent. If you do two, it works because it prints first argument.
No. That wasn't the follow-up question that I asked.
Okay.
How do you know that when args has only one element, it's the first overload that is being called?
Like how the compiler knows, or
no? How do you, as Niels, know that the compiler will choose the first overload if on line 14, args has only one element?
Because James said it and you said yes.
Well, that is true. Okay, that is true. Thank you for your detective work. Well, here is the reason. There is a rule, right? There is a rule that says templates are always well, actually, no, this is not just about templates. Overload resolution in C++ is always based on best fit strategy, right? Now, if it would have been that calling the call on line 14 with just one argument would have wanted to be a call to this, then the compiler had to figure out T, and it had to also instantiate the types, the parameter pack to be an empty pack, which is possible, right? But this would have been a better fit because then it would only need to do one thing, which is deducing T. Okay, so that's less work for the compiler and it's a better fit. That's the reason why if we make it, if this call is with just one argument, then it's always the first overload that wins. Okay. Now, so remember, Jan, that you said that okay, this is a type level list, and I said no, it's rather a type level vector. Here is a presentation of why I said that. There is something called size of ... or ellipsis, which gives you at compile time the size of this parameter pack. And obviously the size of the parameter pack at the type level is the size of the parameter pack at value level because of this. Right? Now, having said that, if you want to program on the basis of this size, let's say having a particular condition, for example, here the programmer is relying on the size being greater than 0, and they perform the next call, right? So what they're doing is that they want to only provide one overload, and only perform the recursive call when there are more arguments to take care of. Right? If you do this, then this if, even though this is a compile time expression, this if is still a runtime if, which means that the compiler will try to compile this bit and produce the runtime code for it. And for that reason, this the compiler will stop you regarding this if.
Since it's runtime.
Correct. Right? Now, there is a way to ensure that this if is evaluated at compile time. Now, let me see whether I have the syntax handy. Oh, I don't. Okay. So there's something called constexpr that I have already told you about, and you can say that this if is constexpr, right? Now I always forget the syntax for that, but I think it's if const expr. Let me just quickly double check that. By the way, there is a website that I was about to introduce to you in the practice sessions. Ouch. Right. Now, this is like the official website, the official reference for C++, cppreference.com. So I'd like to go for const expr if oh, there's also const eval if now. Oh, I didn't know that. Okay, well, you know, so this overload if const expr is when the condition, so provided that the condition is a compile time expression, this if is evaluated at compile time, as a result of which the if statement that I showed to you here, and are you still seeing my slides?
Currently, no.
Seeing
Okay,
your yeah.
Right. Then let me add this. I actually forgot to add it. I just okay. Now, if I put a if I replace the if with an if const expr, then this if statement, given that the condition is a compile time expression, and the if statement will be evaluated at compile time, but the which means that in the condition when in the situation where this condition fails, this if statement will be removed by the dead branch, by the dead code elimination of the compiler, which means that the code that is inside the if statement will not be compiled, which means that there won't be any error messages. Right? Now, I just noticed that there is from C++ 23, there is also if const eval, and this one means that the if statement will always be required to be evaluated at the compile time. Right? This is not so. If the condition that you're providing is not, if it is not possible for the compiler to evaluate the condition that you're providing at compile time, then it produces an error message. Right? That's the difference between const eval and const expr. Now, const eval is a relatively new concept. That's the reason why in the book there is no such thing. Okay. Now, please go away. Okay. Now, the book speaks about the reasons why Variadic templates came to existence, and it gives a number of examples. So two specific examples was that people wanted to do shared pointers. Are you familiar with the concept of smart pointers?
Yeah.
Okay. So one of the common smart pointers is shared pointers, and so people wanted to have constructors for shared pointers in which they would pass the the list of the arguments that they want to pass to the constructor of the underlying type. And they wanted that to be possible for it to be variable for this list to be variable according to the number of arguments that or parameters that the constructor of the underlying type takes. This is one of the compelling stories. The other one was when you have threading. So usually when you have threading, you want to call a function with a number of arguments, right? And the number of arguments depends on the signature of the function, and you never know that in advance, right? So the thing is that this has to change. So that was another compelling story when they wanted to propose to the committee that we need Variadic templates, right? And there is something else called perfect forwarding. I'm not getting into at this point, but you can actually read it. It's good read in the book. And we have to think, by the way, I have to tell you about the book and also my slides. We'll do that after I'm done with the slides. So just like there are Variadic templates, because we have a pack, we can perform unpacking on demand, right? Now, so suppose, forget about this line for a moment, right? Suppose that you have a function print that takes, suppose you have a function print double that takes a number of types as its type arguments, and also takes a number of arguments of those types. And what it does is that it first adds each and every of those arguments to itself and then prints them, right? Now, this is how you would do so. You would say that, okay, I want to have args plus args, and then you place the ellipsis right after that. This means that the recipe for only one of the elements in the list or in the pack is this, but you also do it when you're performing this call for the rest of the elements of the pack, right? Now, I will give you an example so that probably you will be less confused, but I have to say that ellipsis, and especially when it comes to Variadic expressions, can be quite tricky. Now, I'll give you the right place in the book to look into. I should actually have included the table in my slides, but let's see one example. So if I perform this call with these arguments, so we have 3 arguments here, which means that args here on line 2 upstairs is a pack consisting of 3 arguments. Okay, now those are 7.5, string of hello, and complex float of 4 and 2. Now, according to this recipe, this line 4 with this call is equivalent to print of 7.5 plus 7.5, string of hello plus string of hello, complex float of 4 and 2 plus complex 4 and 2. Right? Now, you can also see one thing here, which you know, there is no distinction between built-in types and other types. And one thing which I'm not showing here, but is also the case, is that Variadics, template Variadics are the same for type parameters and non-type parameters. The template type parameters and non-type template parameters. Which means that if your template takes at the type level, instead of a type name ... for example, int ... you can perform similar unpackings using Variadic expressions with your non-type template parameters, right? Niels, you look a bit confused.
No, I'm just trying to kill a yawn.
Okay.
Yawn, not Jan.
No,
Yes,
no.
I got it. Yeah, okay. I'm not going to counting. I'm not going to count it. So don't worry. You managed to. Yeah, you managed to. Now, so thus far, we had only seen function templates with Variadics, but it's also possible for us to have class templates with Variadics. So, for example, you might want to have a variable length tuple. So, you know, you might want to have a tuple that takes an integer and a string and a char, sorry. And you can have that at the same time that you can have a tuple of one or more of these things. And you know, the way you would do that is that you would say, if provided that this is going to take types, then you can say that, okay, I want to this class tuple to be type parameterized by a number of types, right? And then you get the pack there for you as the class template. Now, this is the basis of the project that I'm going to give to you, and we're going to start together in the practice sessions, right? Okay. You can also use Variadics as base classes. Now, how many of you are familiar with the C++ object orientation? Okay, fair enough. So I'm going to go through some of that. Now, probably you know that object orientation has two very important building blocks. There is encapsulation, right, which means that you know, a class is something that you know, has some data members, and it has some member functions, right? And you put all of that together under a box, which is going to be the class, right? Now, when C++ introduced this notion of class on top of C, so it was called C with classes, if I'm not mistaken, right? Back in the late 80s. The keyword class was meant to be different from struct, right? But later on, they came to realize that there is no reason for the two to really mean two different things. So nowadays, the difference between class and struct is not that structs cannot have member functions, they can only have data members, right? The difference is that in struct, everything is public unless you name it private, whereas in class, everything is private unless they
You
are
name it
named
public.
or protected. Now, so this is the first kind of important concept in object orientation, so long as C++ implements it. The other one is a matter of runtime polymorphism or inheritance. Now, inheritance is when your classes or your structs inherit from one another, and you can
Use
pass
the properties. Oh,
that too, but let me see. You can pass. Now, if I could have had my remarkable today, this would be very helpful, but unfortunately I don't. So
do you have a? I think you have a pen tool. If you'd like to draw with a
I
mouse.
do. The Wacom. I right. Oh, the pen tool. You mean these things here?
Yeah, I think.
Well, that would be me, drawing on the
with
on
the
mouse pad.
Yeah, that's
And
nice.
that will not read well.
Mm.
So I'm not going to do that. But instead, what I'm going to do is to show you something in code. So let me make a new share. Anyway, I'll until this comes up. So you can pass when one class inherits from the other one, you can pass instances, pointers to instances of the derived class as pointers to instances of the base class, and also references. So the same goes for the references. Now I'm going to show that to you in action. Strange. Okay, let me now make a new share. Okay. Now this is Code Blocks. It's the editor that I often use for C++. Now let's say that I have a come on. Say that I have a struct base and another struct called derived, which derives from base, right? And this is the syntax for saying that it derives from base. Now then, if I and let's say that I have a function, I can't see my cursor. This is for some reason the coloration is not what I have chosen it to be, but please bear with me. So let's say that I have a function that takes a base pointer and does nothing with it, right? Now, if I have a drive pointer, right? I can call f using dp because dp is a pointer to the derived, right? Which also is a pointer to base, right? Now, yeah, I'm getting a warning here which says that, look, dp is not initialized. I can, if I want to, I can do this so that that goes away. The same is the case if it would have been, so if I, let me just show it to you. If I have another function which can't see my cursor. If I have another function which takes a reference to base, I can pass the dereferencing of dp as the argument to that function, because every reference to a derived pointer, sorry, every reference to derived is also a reference to base. This is you know, the is a relationship between two types. So an instance of derived is a instance of base. You know, these are the two principles of object orientation, and the syntax. Well, I said all of that for you to get to know this syntax. You know, if you're putting a colon between the derived and the base at the definition of the derived struct or class, you're saying that there is a public inheritance, and you don't really need to, for this for the sake of this module, to know what it means to be publicly inherited. But technically, this is only a public inheritance. Now, you're saying that there is a public inheritance relationship between derived and base, right? Now, this I wanted to say because I wanted you to be able to read through this notation. So the interesting thing here is that this struct called overloader takes a number of type arguments, type parameters, and then it derives or inherits from all of them, right? Now, the other thing is that it's trying to use, or it's trying to pump things from its ancestors into its own namespace by doing things like this, using base : this means using things from base, right? And in particular, it's pumping operator parentheses of. And well, again, this is something that I have to show to you because I think that you don't know enough C++ for this. So let's see. Let's say that I want to be able to do this. I want to be able to call, so let's say that I want to have a base B, and I want to be able to say B of I don't know, 14, right? Which means that I would like to be able to call or pretend that I can call an instance of base, right? The way to do that is by providing what is called a function call operator. So and let's say that it takes int, and let's say that it's going to see out what it gets, right? Now, with this, oh, yeah, let's say that it returns, let's say that it does something else. Let's say that it returns in time, so that I don't get the warning that I was getting. Now, so what this line is saying is that, you know what, if someone uses B an instance of base in this way, which means that they want to perform function calls on the instance, then this is the recipe for them, right? Now this is saying that, okay, the function call syntax given a variable n for an instance of base returns n times 3, right? Now,
sorry, can you repeat that? Just
of course, the syntax
one
is
more time,
bizarre.
one more time.
Yes, the syntax is obviously bizarre. I mean, I'm not surprised at all that you couldn't follow it. This line 7, right? The line 7 is saying that if the user of the class base or the struct base wants to do a function call syntax on instances of base, and the function call syntax is this. This is the function call syntax. This is a special function.
There's an underscore. That's fine.
No,
There's an
no
underscore?
There's
no,
no
there
underscore.
isn't.
What?
It's a space, and the highlighting, the syntax highlighting is awful. I don't know how it managed to change, but I'll get it back when offline, right? Now, anyway, there is a space between the keyword operator and the pair of round parentheses.
Right, yeah.
Right. So what this is saying is that the function call syntax on instances of base works provided that they pass an integer, which I'm going to call n.
Yeah.
And if I pass that, I will return n times 3.
What's your const doing?
Yeah, I was wondering the same thing.
Doing?
Const.
Right. Okay. Maybe I should have not put this. It's the same. It would be the same here, right? But since I did show that, I will also explain that to you. Right. What the const is doing is that it's saying that performing this function call will not manipulate the instance on which the function is being called.
Oh, as in, wait, it will not manipulate base?
No, it will not manipulate this B here.
Yes, that's what I meant. Right, okay.
Right.
Okay, and can I ask, because I've done operator overloading before on classes, a surprising amount, but the syntax was a bit different. Is because I had like operator, I didn't have maybe I could have had the space.
I think, well, yes. I mean, you can. In fact, there's
think-
no need for there to be a space.
Ah, okay. Now it
That's
looks
why.
more familiar.
That's
Yeah, yeah,
okay.
yeah.
Okay.
The
All
space is so
right.
nice though.
Yeah.
Genuinely thought, because now now it looks like there's some special overloaded. I didn't
Okay.
realize operator was a keyword.
No, it is. It is a keyword. Yes.
Mm.
My mind is you've smashed some worlds into one another.
Oh,
So-
I've done this so
Ex-
much and not realized what I was doing.
You've expanded your horizons, James.
right.
Oh,
That's how you
very
managed to do that.
Yeah,
Just
very
with a
good.
simple space.
yep.
Right. That's the gap between the two words.
There's no. You have
Right.
reached synthesis.
Yeah, James, I had the impression from the day one that you said that you do the C++ and the Haskell and your Haskell was faster than your C++. My feeling of GOTS was that you are not at all exposed to good C++.
I disagree with that.
And this is a perfect presentation.
I will.
There is nothing wrong with you personally on that, but I can see clearly that you are not exposed to good C++. Yeah. Now, let's get back to the slides. Oh, right. Now, here there is a glitch. So if I want to do okay. Let me do something else. This is scary syntax. If I want to do this, right? Let me put it like this for you. Why do you think the core on line 25 is doable? And I'm going to ask that question from Sander. Why is the core on line 25 doable? Do you understand the syntax at all?
Like halfway? Yeah, it's a pointer, right?
What this is doing is that it is dereferencing DP. Now, DP was a pointer to derived, right? Now, dereferencing the pointer will give us a reference to derived. Now, a reference to derived is also a reference to
Base.
base.
Yeah.
And base has an operator as a function call operator overloaded, which means that this call is doable.
Right. Okay.
However, let's say that I have a derived D, then I'm gonna now do this. What do you think the difference? And this is I'm gonna put this one to Jan. What do you think? What do you think the difference between line 25 and line 27 is?
You're not making a reference anymore. It's
very good, very good. This is no longer a reference.
Yes. It's directly to derived.
That's true.
And derived goes to base. But I'm not sure.
Right. Now, derived inherits the the
Operator
function
from
call,
base.
yes, the function call operator from base, right? However, there is something subtle going on here, which I'm not showing in this example. There is slicing going on. Right now, and this is for you to put a research on. Right now, it is true that pointers and references to derived classes are also pointers and references to the base classes. But here, right, D is not a reference. Right? So this is correct. This is rather a call by value rather than call by reference. Right? And as a result, when the call is being performed, only the B sub part of D is going to participate in the call. And if I had my remarkable, I would have drawn you some pictures. Let me see whether I have
the B
something.
subcall of. Okay. B subcall of D. But B, how does D call B? B is referred to above, but there is no connection between D and B.
There is a connection.
Is it just the fact
the
that
connection is that sorry, I think the base part, sorry, only the base part of D, not the B part of D.
Okay, yeah, the base part, yeah, that makes sense. That makes sense.
Yes, only the base part of D is going to participate in the call.
Because that's the one that has been function overloaded. It's the one that has the the operator round brackets.
And it's for that reason that if you go to the slides, and this is something in the book, it's for that reason that this guy is trying to pump the that's a very long yawn now, Niels. You have been fighting against it for a long time. Yes. So right. This is the reason why with line number 4 here, we are trying to pump the function call overload of the bases, all of them, into the scope of the struct called overloader, because we are trying to defend ourselves as the programmer of the overloader against slicing. Right? Yeah. Now, I think this is pretty much it. Yes. Are we done? Daniel, I think that the last few minutes of this is my impression. The last few minutes of today were particularly confusing to you. Is that so?
I don't think I've fully grasped
okay.
the issue, but I've made a note of it now, at least to work on it.
Is there any question on this that I can maybe answer right now? Do you have specific questions? No?
No, nothing specific.
Okay. No problem.
I'll try to think of something for next session.
Right. So you will need to go through a number of things and do a lot of reading, I guess, maybe, until you are up to the level where you can digest what I just said. Yeah. Okay. But if you ever get stuck, just let me know.
Of course.
Okay. Now, so that's the end of